In this video, we'll be doing some more examples on two-phase method for solving linear programming problem. In my last video, I have defined what is phase 1, what do I mean by auxiliary LPP. So an LPP with the same constraint that is given in our linear programming problem, but with the new objective function, and the new objective function is the sum of the artificial variable. This is what we want to minimize. So we can have, and we want to solve this LPP with the normal simplex iteration, that is having the Zj minus Cj should be greater than equal to 0 for the maximization problem, and this is for the minimization problem optimality criteria, and we apply the row operation. So with that we can get these three cases, and in the first case we say that minimum of Z star is strictly positive and artificial variable remain in the basis. Then we conclude that there is no solution or the LPP have infeasible solution. So in my last video I have covered an example for this case. Now in this video I want to cover the examples for case 2 and 3. And in case 2 and 3 the Z star value is a 0. So the first possibility is that no artificial variable remain in the basis. That means here artificial variable is acting as a non-basic variable. So if it is out of the system, it is not appearing in the table. So in that case, artificial variable is acting as non-basic variable. And we know that non-basic variable always take the value 0. So we have to move to phase 2. And in the third case, we want to say that artificial variable appear in the basis, but at 0 value. So in this case, artificial variable behaves as a degenerate basic variable. And then also we go to phase 2. So in phase 2, we work with the original objective function. Now let us take the example for case 2 and case 3. So consider this problem, and I want to use two-phase method to solve this linear programming problem which has the objective function as minimization. So the first step is to always write the LPP into standard form by involving the artificial variable. And as we are applying with the two-phase method, so I also want to write the auxiliary LPP, and hence writing LPP into standard form and involving artificial variable wherever they are required. So I require them in the first and second constraint because the identity column is missing in first and third constraint, and in the second it is available due to the slack variable. So the objective function becomes minimize Z star equal to A1 plus A2. So this is sum of the artificial variable which I want to minimize, and this is what is the auxiliary linear programming problem. Now I want to solve this with the simplex iteration in the usual manner in the phase 1. So we write the basic variable as the A1, S1, A2. So these are the first set of the basic variable, and we know the cost of the basic variable, this is plus 1. And the slack variable, this is 0. And then we write all the coefficients that are available in the given matrix directly here, because now we have the ready identity. So this gives 5 1 0, 10 0 1, and here I get 0 1 0, 0 0 minus 1, and we get the identity columns corresponding to this. This is the right hand side of the constraint which maintains the feasibility. And then we write the value for Z. So Z is multiplication of XB column, this column, multiplied by the cost of the basic variable. So we can see that 150 into 1 plus 20 into 0 plus 14 into 1. So that is how I have written Z. Now to write Zj minus Cj, I have to follow multiplication of scalar by CB vector minus the cost of these decision variable. And that cost of the decision variable must be taken from this current objective function which is in auxiliary LPP. So when I multiply 5 into 1 plus 1 into 0 plus 0 into 1, so that gives me 5. And we can see that there is no x variable here. So the cost of the x or the SI decision variable must be taken as 0. So this first Z1 minus C1 is 5. And similarly I have calculated the other one. So this will give me these values. Now we see that whether the current table is optimal or not as per the standard Zj minus Cj criteria, and we see that objective function is minimization, so the most positive will enter. The optimality criteria must be Zj minus Cj should be less than or equal to 0 for every j. Till the time we do not have this condition, we have to keep on entering and find the corresponding leaving variable. So we enter this one and we find the one that is with the minimum ratio. So with the minimum ratio, we'll leave this one because the ratio will be checked between 10 and 1. So this is 150 by 10 and 14 by 1. And so 1 becomes a pivot element. So using the row operation, I have A1, S1, and instead of A2, now I have X2 variable. So X2 variable will give me always 1, 0, 0, 0. These are corresponding to the basic variable. So we can fill out these column quickly. And S1 will correspond to 1 and all the other entries are 0. But we need to fill out the operation keeping this one in mind and these elements in mind. So let us write down the row operations. So R1 goes to R1 We see that here it is 11, so R1 minus 11 times with the help of pivot, and pivot is in the 4th row, so this is R4, and R2 goes to R2 minus 10 times R4. Then R3 remains as R3 because you can see that already it is 0 and I require a 0, and R4 also remain as R4. So keeping these rows fixed, I get these entries now in this next table as, so this is 5, 5, 1, 0. And then corresponding to S2, we have 10, 10, 0, minus 1, and this is minus 10, minus 10, 0, 1. And in the last column, we got 10, 10, 20 and 14. And for the faster calculation, you can see that whenever the surplus variable is appearing corresponding to the artificial variable, or I may say artificial variable is appearing to the corresponding surplus variable, they both variable differ with a negative sign, and otherwise their coefficient is same. So in the scalar, when we do the calculation, if it is 0, 0, minus 1, here it is 0, 0, plus 1. And if it is 0, 0, minus 1 here, so this is minus 10, 0. So they only vary with the negative sign. So you can calculate the one column in the row operation and fill out the other with the negative of that. So that way we can fill out the column and we can reduce our manual calculations. Now in the current table, Zj minus Cj is still not less than or equal to 0 as per the minimization objective function. So enter the most positive, that is 10. And by the minimum ratio rule, we have to leave A1 because this is the only positive scalar. And we get next table using these row operation as this, and I've replaced artificial A1 with the variable S2. So now you can see that current simplex table, which is this one in the phase 1. So this satisfies the optimality criteria. Here Zj minus Cj are all less than or equal to 0. So, and obviously these are feasible. Feasibility will always remain maintained because this is because of the minimum ratio rule, and we have not violated minimum ratio rule. So the current table is optimal. So the phase 1 end, we can say that phase 1 ends. Now in the phase 1, we have to also see that whether artificial variable is in the basis or not. You can look that in the artificial variable is not in the basis, and the value of Z star is a 0. So when we say that minimum of Z star, because our objective function is minimization, this is a 0. And artificial variable, this is acting as a non-basic variable. So this is a non-basic variable. So we have to go to phase 2. So now I move to phase 2 and from the phase 1, and in the phase 2 I'll use the last table of phase 1. So for that, let me to write down the table as, and in this table we need to now write the original objective function. As you can see that now work with the original objective function, which is this. So minimization of Z equal to 2x1 plus 8x2, and here the slack surplus variable has a cost as 0. So in that basic variable, let us now write the slack variable cost and the surplus variable cost is 0, and corresponding to x2 we have 8. Now I want to calculate Zj minus Cj, which I will write here, and also the value for Z. So for that I am going to use the formula multiply with the xb vector with the CB vector. So this will give me 15 into 8 plus 20 into 0 plus 1 into 0. This quantity will be 120. And I also calculate Z1 minus C1. So multiply the scalar with this one and subtract the cost of the original decision variable, that is this one. So 0 into 1 by 2, 0. 0 into 1 is 0. 8 into 1 by 2, that is 4. Minus this 2, so this is 2. And in this way, I calculate all the other values for Zj minus Cj. Now look at this Zj minus Cj and the current objective function. In the given LPP, we have minimization, and at this stage Zj minus Cj are greater than or equal to 0. They are not less than or equal to 0 because for the optimality, even in phase 2, I require this one. So I enter most positive. At this moment 2 is most positive, and we find the corresponding leaving ratio. Here S2 leaves the basis and 1 by 2 becomes a pivot element. So now we perform the simplex iteration as usual and we get this table. And here I have written the value for Z, and in the earlier table this was Z star. So Z is this is feasible, and the current table is optimal. And we say the optimal value, originally we want minimization objective function, so Z minimum is 116 at x1 equal to 2, that we can see it from here. X1 value is 2 and the decision variable x2 is equal to 4. So this is the optimal solution of the given LPP, and you must have noticed that I have not written artificial variable here. I have not carried these artificial variables in the two-phase method because once they leave the basis, their purpose is fine. We wanted to know whether the current table gives us a feasible solution or not. Once we move to phase 2, that ensure that there is a possibility of the feasible solution. So we drop these two artificial column in the phase 2, and in this way we can find the optimal solution using the two-phase method. Now consider this problem, and I want to solve now this problem with the two-phase method, and here the objective function is maximization. And notice that here I have considered all equality constraint. In fact, this x3 and x4 decision variable, they are the surplus and slack variable respectively, because they are not appearing in the objective function. So we can see that this is 0 into x3 plus 0 into x4. So s1, s2, these are just notation. We can even write the slack surplus variable as the x size variable. So now let's solve this problem with the two-phase method, and as the standard procedure, we first write the LPP into standard form by involving the slack surplus artificial variable. Here we do not need to involve slack surplus variable, it is already inequality. So just involve the artificial variable. Construct the auxiliary LPP and write this simplex table corresponding to the phase 1. So here I have written the LPP into auxiliary LPP with the objective function as minimum z equal to a1 plus a2. I have added the first artificial variable here in the first constraint and in the second constraint, because x4 acts as a slack variable, so we do not need to add an artificial in the third constraint. So with this procedure, I have constructed now the normal simplex iteration phase 1 table, and here I have only written the last table of phase 1. So I have started initially with basic variable as a1, a2 and x4, and then perform the normal iteration, and I get this table as the last table of phase 1. So in this last table of phase 1, we notice that artificial variable is appearing in the basis at 0 level. So, and z star is also 0. So this address to our third case that artificial variable appear in the basis at 0 level or with the 0 value. So this is the case of degenerate basic variable, and this also allows us to move to phase 2. So now I'll construct the phase 2 table, and in the phase 2 I want to work with the original decision variable. So here we need to drop this artificial variable a2, and we do not want to carry this in the phase 2. So for dropping this, let us look. These x1, x2 are already basic variables, so they are already in the basis x1, x2, so we are not removing this one. Artificial variable, we have to drop this from the basic table, and the only possibility is x3, x4. So instead of this artificial variable a2, either we can introduce the non-basic variable x3 or the non-basic variable x4. So here we intentionally enter any one of them. So we can choose either x3 or x4, anyone. These are the non-basic variable. So introduce these two in the next table of the phase 1, so which is the first table of the phase 2. So we enter either x3 or x4. Suppose I choose to enter x4, and here I have to remove artificial variable a2. So the only possibility is that this will become the pivot element. Now this is not with the minimum ratio rule. As you can see that here I have selected a scalar which is -1 sign. Here we are only trying to replace a non-basic variable with an artificial variable, because the purpose of the artificial variable is ensure that it is possible to give us a feasible solution, and this replacement will not lead us to infeasible solution in the next table, because the next table will give me the calculation 0 upon this scalar. So it is 0 upon -1, which is further 0. So this does not disturb our feasibility. So using the row operation, I'll fill out first this table, and here I will leave the z row, because the z row is calculated with the new objective function, not with this one. So for the calculation of the z row, I'm not using the row operation. I'll consider this as R1, R2 and R3. So with this in mind, the new row operation will give me R1 as R1 plus 1 by 5 times minus R2. That is the pivot row. R2 goes to minus R2. You can see that here it is -1. And R3 goes to R3 minus 3 by 5 with the help of the pivot row, which is -2. So using these row operation and noticing that x4 comes in the basis, so we fill out these entries, and also we know that these are basic variables, so you can directly write the identity columns also. The only thing that I need to calculate now x3 column with the help of these row operation, and I'll calculate zj minus cj with the help of the formula. So let me to first write down the entries which will come here. So this is 1 by 5, 1 minus 3 by 5. So if I want to verify this minus 3 by 5, which is corresponding to x3, so you can see that corresponding to x3 value, we have this -1 and 0, and -1 was the pivot element. So in this case, R3 value, this is 0. This is the R3 value, minus 3 by 5 times minus of R2, which is -1 here. So this is minus of -1, that will make it +1. So this value is -3 by 5, and hence we have written -3 by 5. And on the right hand side we have 3 by 5, 0, 6 by 5. Now to calculate the z row, let me to write the cost from the original objective function. So the cost of x1, this is minus 2, the cost of x4, this is 0, and the cost of x2, this is minus 1. So multiply this by this one and subtract from the original cost. So this will give me calculation as minus 2 into 1 minus 2. These are basic variables, so this has to be 0. Let's calculate for x3. This is minus 2 into 1 by 5 plus minus 1 into minus 3 by 5 and minus the cost of 0. So this value is 1 by 5. And similarly multiply this xb with the cost vector to get the value for z. This will give me minus 12 by 5. Now we have to see the current zj minus cj. The current zj minus cj are all greater than or equal to 0. So, and the given objective function is maximization. So this is optimal. So hence we get the optimal solution z maximum as minus 12 by 5 at x1. This is equal to 3 by 5 and x2 is equal to 6 by 5. x3 is not appearing in the basis, so this is non-basic, and x4 is also non-basic variable. This takes the value 0. So this is the optimal solution for the given linear programming problem. Let us consider one more example for the degeneracy case. In this problem again I want to solve this LPP with the linear two-phase method, and here we have objective function as maximization. I have constructed an auxiliary LPP by involving artificial variable. Artificial variables are required in the first, second and third constraint because x4 is appearing here and it is not appearing in the previous column. So this is actually like a slack variable. So I have now the four basic variables for the first initial table a1, a2, a3 and a4. And with the usual manner, all variables greater than or equal to 0. And so we can construct the phase 1 first table. And here I have only shown the last table. So the other calculations are usual. I am sure you can construct the other table. So this is z star. So in the last table I got z star as 0. So you notice here this is 0 and artificial variable is appearing in the basis at 0 level. Now as I did in the previous example, I have replaced the artificial variable with a non-basic variable. So let us see here. x1 is a basic variable, x2 and x3. These are basic variables. So this is already in the basis. And then artificial variables are not going to forward in the phase 2. We do not want. The only possibility is that this x4 is a non-basic variable. So we can do the replacement with the non-basic variable only. And now if I enter x4 into the basis and I remove a3 from here, so we see that pivot element is a 0. Now this is not allowed because 0 by 0 is not defined. So when I construct a next table by replacing like this, x4 is entering and a3 is leaving, here the pivot element is 0. So this replacement is not possible. In my previous example, we have a non-zero quantity. So that replacement was possible. So in that case, we simply have to drop this row. So simply delete this row and rewrite the table with x1, x2, x3 into the basis. Here you can see the basis size has reduced. We have 4 constraints. But in the basis, finally, we have written the 3 basic variables. And this is the same table corresponding to these entry 1, 0, 0, 0, 1, 0, 0, 0, 1 and 1 by 2, 3 by 2, 1. So this is corresponding to x4. So these artificial variable columns we have dropped and the right hand side. So I have written now the new CB vector as per the original objective function. And I have written zj minus c0 the corresponding, and I find that this is non-negative. So this is zj minus cj non-negative as per the objective function, which is maximization, and z equal to 4 is the optimal solution, optimal value with these solution, and we got this as the optimal solution. Now let us see why I have cancelled this row. What is the reason behind this? Here this problem is redundant. Redundant means, let us see here, one of the constraint is appearing as a linear combination of the other one. Notice that the first and the second constraint, if I add this first 2 constraints, so this x1 will get cancelled. This will become 2 times x1, which is here. x3 plus 2 times x3, which will become 3x3. And if I add 6 plus 4, this will give me the value 10. So the addition of the 2 constraint is the third constraint. So that means the third constraint acts as a redundant constraint. If we remove the third constraint, this is fine. So this dependency, so that means corresponding to this, the third artificial variable which is appearing in the basis. So in the first simplex table, third artificial variable appear in the basis and this is acting as a 0. So this has to be removed. So this is why I have cancelled now this redundant decision variable, and it has to be removed. This is not appearing as a linearly independent basic variable. So this redundancy come when we have an entering variable and corresponding to artificial variable which appeared at a 0 level, the pivot element is a 0. So if this pivot element is 0, we are going to simply cross off because of this redundancy nature, and hence we get the optimal solution as per usual case.